Undoubtedly, the cosmos presents us with the greatest number of enigmas. Solving them isn't easy, but nothing prevents us from developing a series of hypotheses that are more or less close to the truth. Admittedly, even with today's technology, it's still quite difficult to answer some questions. For instance, what are the dimensions of the universe, and does it have boundaries? Progress doesn't stand still. Therefore, our understanding will soon expand significantly as new generation telescopes are coming online. These telescopes, I'm confident, will open the gates to the murky past of the immeasurable universe. In a short time, people will see the world not only through the eyes of the Hubble Space Telescope. 2 years from now, the world's most powerful infrared observatory, the James Webb Space Telescope, will become operational. Thanks to this apparatus, launched into orbit, we will be able to find exoplanets, observe the formation of galaxies, and the birth of stars. Besides it, the PLATO telescope is being prepared for launch, designed to search for super-Earths and capable of blocking the dazzling light of stars. An X-ray telescope with highly sensitive detectors is also under development, capable of detecting locations where black holes are formed. Further advancements include a telescope with a huge 9-meter mirror and hardware 30 times more sensitive than the James Webb Telescope. Thanks to these technological achievements, we can examine Proxima b, located near the star Proxima Centauri, 4 light-years from us, in more detail, as well as Kepler 16b, the prototype of the legendary Tatooine. Moreover, astronomers will be able to observe the hellish lair of Satan, a planet where one hemisphere experiences constant daylight and the other perpetual rain. Let's consider another interesting question. How can a person, accustomed to Earth's relatively small size, comprehend, much less measure, billions of cosmic kilometers? It's obvious that it's extremely difficult for an Earthling to imagine where the aforementioned planets, on which life might exist, are located and how far they are from us. Therefore, let's have a quick primer on the units used to measure distances in space. Within our solar system, this is done in astronomical units. 1 AU is equal to the average distance from the Earth to the Sun, that is, 150 million kilometers. But beyond the solar system, it becomes extremely inconvenient for scientists to count dozens of zeros. Therefore, a unit of measurement like a light year comes into play. It encompasses the distance that a photon of light travels in 365 days. The speed of light, if slightly rounded, is 300,000 kilometers per second. The result is a huge number with 12 zeros. Considering this information, it's frightening to think about the distance of Proxima b from us, one of the closest exoplanets discovered. This information can activate the imagination, conveying the scale of these distances. To better grasp these scales, let's try to measure a light year in terms of human steps. This sounds strange, but try to abstract and imagine what will be discussed next. For example, through simple calculations, we can find out the following. If a person moves continuously for a year at a speed of 5 kilometers per hour, they will cover a distance of 43,800 kilometers. Now, let's take the average life expectancy of 68 years and multiply it by the above figure. We get 2,978,400 kilometers. That is, if you walk without stopping your whole life, you will travel about 9 light seconds. Think about it. A person won't even reach Mars. But as the saying goes, many hands make light work. So let's calculate how many kilometers the Earth's population would cover, splitting into pairs and passing the baton to the next tandem every 68 years. The figure turns out to be much more tangible. As you can see, it's even more than a light year, but the entire planet would have to walk for millions of years. Now think about how many people and how much time it would take to walk, say, to Alpha Centauri Bb, located 4.4 light-years from us. And if you try to cross the Milky Way, which is 100,000 light-years in diameter, your hair will stand on end. It's not even worth trying to calculate the person-hours required for a pilgrimage across the largest known galaxy with a diameter of 6 million light-years. We can say for sure that it's not enough to have the efforts of all the people who have ever lived on Earth, which is about 107 billion people. If the distances to individual parts of the stellar planetary community are so vast, then how immense is the universe itself? No one living on Earth can say for sure what its dimensions are or whether the macrocosm is finite. But one undeniable fact is known. The sky we look at every night is a kind of video recording, in other words, a glimpse into the past. The question is only about time. Sometimes it's only 8 minutes, as in the case of the sun, and sometimes millions and billions of light years. That is, the glittering object you are now looking at may be a galaxy that died many centuries ago, but its light will continue to travel along cosmic highways for a long time. To conclude, let's address another topical problem of cosmology. What is the limit of the macrocosm we cannot look beyond, and what objects can we observe relatively unimpeded? It is known that the boundary of the observable universe is approximately 45 billion light-years from us. This is incredibly far, but what lies beyond this horizon? Humanity will likely lift the veil of this mystery, but not soon. It is worth mentioning the hypothesis of the uniform expansion of the universe, often discussed in scientific circles. It is generally accepted that this occurs uniformly at all points simultaneously. Therefore, it is impossible to understand where you are now, in the center or on the periphery. This means that the horizon may recede over time, and even after thousands of centuries, telescopes capable of peering beyond the invisible boundary of the Titanic bubble and seeing what lies in the inky blackness of space are unlikely to appear. Neither Hubble, nor James Webb, nor any existing telescopes are capable of this, let alone future ones. Fortunately, there are so many interesting objects around us for study that it will take entire generations of astronomers. Contemplating the boundaries of the universe, while tempting, is not very productive. If you are interested in this topic, write your thoughts in the comments. Perhaps you adhere to the multiverse version with alternative laws or believe in an infinite, flat macrocosm. Or maybe you are a supporter of the hypothesis that humanity lives inside a giant black hole. Everyone has at least once in their lives observed how a silvery streak cuts through the inky night sky, left by a passing comet. Where do these mysterious celestial wanderers appear in the solar system? It turns out they have a habitat called the Oort Cloud. Traditionally, many people imagine the solar system in a significantly truncated form, limiting its size to planetary orbits, but this is not so. According to the vast majority of astronomers, the Oort Cloud constitutes the outer boundary, located approximately at a distance of 100,000 astronomical units from the Sun. The existence of this global formation cannot be definitively stated, since its presence has not been instrumentally proven. However, indirect signs confidently indicate that the Oort Cloud exists and most likely serves as a kind of supplier of cometary material. It is assumed that the Oort Cloud is a titanic torus, the outer boundary of which coincides with the gravitational boundaries of the solar system, located at a distance of 1 light-year from our parent star. This imaginary line is called the Hill sphere, the space of gravitational influence exerted by a large object on smaller celestial bodies. The Oort Cloud is home to trillions of comets formed at the dawn of the solar system's formation. But what knocks them out of their orbits, and why do we notice their sparkling paths in the sky? Astronomers unanimously agree that comets peacefully residing in the Oort Cloud are most likely affected by external forces emanating from passing stars and the Milky Way galaxy itself. They literally eject these tailed guests into the embrace of the solar system. If we dwell on this issue in more detail, it is worth focusing on 2 hypothetical objects, the gas giant Tyche and the star Nemesis. The latter, according to scientists, is a companion to the Sun, but as they like to say in modern memes, this is not certain. It is extremely difficult to detect it using instrumental methods, since this phantom star revolves beyond the Oort Cloud. If this is true, then such a huge object must undoubtedly influence comets located in the scattered disk. A certain group of scientists associates Nemesis with the periodicity of mass extinctions on Earth, allegedly regularly approaching the Sun. The star disturbs the stability of the Oort Cloud objects, as a result of which a massive cometary rain falls on our planet, destroying developed life forms. As for the gas giant Tyche, which is also believed to influence the orbits of comets, it may be located directly in the Oort Cloud, although it has not yet been discovered by terrestrial telescopes. All this information is presented not just like that. If the specified clouds do exist and are an integral part of the mechanism called the solar system, it is not difficult to guess how closely its internal processes are interconnected with this monstrous structure. Let's return to the description of the Oort Cloud, whose existence was first proposed by Estonian astronomer Ernst Öpik in 1932. 20 years later, a similar hypothesis was put forward by Jan Oort, a Dutch astrophysicist. Later, the object was named after him. Both scientists tried to explain the paradox of the short lifespan of comets, proposing an imaginary reservoir where comets peacefully floated in a vacuum until their orbits were disturbed. The outer boundary of the Öpik Oort cloud was outlined, while the inner edge presumably runs at a distance of about 2,000 to 5,000 astronomical units from the Sun. The structure of different sectors is highly heterogeneous. For example, the inner region has the shape of a disk, and the outer region is a huge sphere. At the same time, the density in the inner part is much higher. Billions of comets rotate there, consisting of water and carbon dioxide, toxic methane, and cyanide. They also contain fragments of rocky planets. The orbits of comets are stable in most of the cloud's space, and only in the outer sector are they chaotic, since, as mentioned earlier, they experience periodic perturbations from external objects. How did the Oort cloud appear? This enormous structure, with a diameter of about 200,000 astronomical units, is a remnant of the same gas-dust nebula from which the planets and other components of our star system arose. It is believed that 4.5 billion years ago, the Oort cloud was much closer to the Sun than it is now. Over time, the orbits of the gas giants pushed the global structure further into space. The Oort cloud reached its maximum mass approximately 800 million years after its appearance. At that time, stellar visitors much more often passed near the boundaries of the solar system. By the way, structures similar to the Oort cloud have been discovered in other planetary systems. Therefore, the appearance of a cometary shower is possibly a typical phenomenon in the universe. As a result, a logical question arises. How dangerous is this huge neighbor for Earthlings? With more detailed study, it turned out that massive stars are not the only ones that can knock comets off course. Galactic tides, like those in other clusters, are characteristic of the Milky Way. They are similar to those that occur on the Earth's surface thanks to the Moon. These phenomena distort the shape of the Oort cloud, perturbing the gravitational field and changing the orbits of comets. It is possible that right now, some comet is rapidly flying towards Earth, but we don't know about it yet. Will humanity ever be able to look at the Oort cloud with its own eyes, or at least with the help of cameras on interplanetary probes? Honestly, considering the incredible remoteness of this structure, this is unlikely in the near future. Currently, the New Horizons Automated Interplanetary Station is exploring the Kuiper Belt, which is much closer than the Oort cloud. But not all is as hopeless as it seems. The trouble is that the human lifespan is very short, so neither we nor our children will see what Voyager 2, which has departed from the Sun by 119 astronomical units, can demonstrate. After 270 years, the probe will reach the inner boundary of the Oort cloud. However, even now, it takes more than 16 hours for the probe's signal to reach Earth. Therefore, from such a monstrous distance, we are unlikely to be able to detect it. For the probe to completely pass through the cloud and finally leave the solar system, it will take 30,000 years. Isn't this a vivid demonstration of the titanic dimensions of this structure? For Voyager 1, it will take a little less time, 240,000 to 27,000 years respectively. However, perhaps in the future, technologies will go beyond current ideas, and we will see the objects of the Oort cloud much sooner than we expect. And finally, perhaps the most pressing question, the answer to which we are seeking in all corners of the universe. Is life possible in the Oort cloud, even at a microscopic level? It would seem that the answer is obvious. At such a huge distance from the stars, this is unthinkable, but not everything is so unambiguous. In 2003, a large trans-Neptunian object was discovered and named Sedna. Given its remoteness, this dwarf planet is located in the Oort cloud. How and when it managed to get into this distant realm is still unclear, but presumably, this spherical piece of ice hides a liquid ocean under its shell. Thanks to internal radioactive decay, Sedna heats up, allowing it to maintain temperatures suitable for the hypothetical emergence of organic life. Around 2075, when the planet reaches perihelion, an excellent opportunity will present itself to study this question in more detail and find out exactly whether the Oort cloud is inhabited. This year's Nobel Prize in Physics is directly related to black holes. In particular, it was awarded to the astronomers who revealed the central black hole in the Milky Way galaxy, and to Roger Penrose, who proved that, according to general relativity, every black hole contains a region of infinite gravity, a singularity. However, the true significance of Penrose's singularity theorem is much deeper than it seems. It forces us to test the limits of Einstein's theory and to ponder the origin of the universe. Black holes have always been, as if, on the periphery of scientific thought. Back in the 1700s, when Jean-Michel and Pierre-Simon Laplace studied Newton's law of gravity, they realized the possibility of the existence of objects so massive that even light could not escape their surface. Very few took these dark stars seriously, especially considering that in reality, light does not behave as described in the works of Newton, Michel, and Laplace. Gravity, in the end, also does not work as the great Newton bequeathed. In 1915, Newtonian theory was essentially replaced by Einstein's general theory of relativity. This was not the end of the story of black holes. It was only the starting point of their study. Karl Schwarzschild solved the equations of general relativity shortly after Einstein published them and proved that a very dense sphere of matter would be surrounded by a surface where time itself would stop. Below this event horizon, all matter, light, and space are doomed to fall inward, towards a central point, the so-called singularity. The gravitational field becomes infinite, but physicists have many questions about infinity. They are often just errors in the theory, not objective facts. Einstein himself doubted that black holes could arise in the real universe, and even if they could, not with singularities. In 1939, Robert Oppenheimer and Hartland Snyder showed that a perfectly spherical star could collapse into a Schwarzschild black hole with a singularity and everything else. This makes sense because if all the particles fall directly onto each other, according to mathematical calculations, they should all land in the center. But this did not convince anyone. Indeed, where in the universe can one find something spherical, so perfectly smooth? It was decided that ordinary objects could never collapse into an ideal point. The slightest deviations from spherical symmetry, and the particles, while falling onto each other, are not pulled to the center. Then we arrive at the 1960s. Roy Kerr had just come up with a way to describe a rotating black hole in Einstein's theory. In it, the central point of infinite gravity is twisted into a ring, but it was still a singularity. Kerr's solution was still extremely symmetrical, so the old doubts about their existence in objective reality remained. This prompted a young Cambridge physicist named Roger Penrose to prove that the singularities of black holes were absolutely inevitable in Einstein's theory. Penrose's scientific work on singularities is surprisingly short, just a couple of pages in the journal Physical Review Letters. However, brevity is the soul of wit, as they say. Some believe that this 1965 work produced the first serious addition to general relativity in half a century since its creation by Albert Einstein. What did Penrose find out? How did he manage to mathematically embrace the essence of a black hole? And why did he finally deserve the Nobel Prize? Roger Penrose proved that, according to Einstein's theory, with a couple of assumptions, black holes must have singularities. He did this by demonstrating a network of space-time that literally comes to an end inside a black hole. In general relativity, we denote spatial coordinates using geodesic curves. The path of a light beam falling into a black hole is called a null geodesic line, or simply a geodesic. This is a kind of gold standard for marking space-time. Null lines are laid through or across the gravitational field, gradually converging to one point. This is called gravitational lensing. Gravitational fields created by ordinary matter always produce this convergence. Negative mass or negative pressure would be required for the rays to begin to diverge. This feature of gravitational fields is called the weak energy condition in general relativity. Thus, the null lines tending to a black hole must converge. There seems to be nothing complicated about this, but there is a strangeness. Null lines beyond the event horizon moving outward, oddly enough, will also converge. The very idea of an event horizon is rather ambiguous and depends on the observer's position relative to the black hole. Penrose proposed a clearer idea, the idea of closed trapped surfaces. Any closed region inside a black hole is considered a closed trapped surface. Penrose stated that at least several parallel light rays leaving a closed trapped surface, moving upward or downward, must converge. In other words, space and time end at the point of focus. Let's try to compare this with a more familiar geodesic on planet Earth. We use parameters such as lines of longitude and latitude. Lines of longitude converge at the north and south poles. Such a line is the shortest route from one pole to another, but you can get a little carried away, miss one of the poles, and start circling the planet anew. Thus, it will no longer be the shortest route. Traveling through a black hole, you will not reach any poles, but you will reach the end of time or space, a kind of dead end of reality. Roger Penrose managed to show that space and time can have peculiar holes. These holes are directly related to infinite space-time curvature or infinite gravity. In other words, singularities. Penrose did not manage to show what type of singularity will form in a black hole. He only found out that its presence there is obligatory. As soon as Penrose published his work, a young student was inspired and supplemented this work in a very unusual way. This student's name was Stephen Hawking. In his doctoral dissertation, Hawking demonstrated that we can use the same evidence to find out the behavior of geodesics moving backward through our entire universe to the Big Bang. For about 40 years, we have known that the universe is expanding and most likely originated in a much less compressed state. We know that geodesics converge with each other moving backward in time, but this does not mean that each of them must necessarily meet another. They can, for example, miss each other while gathering into a sufficiently dense knot. Hawking shows that Penrose's proof regarding black holes also applies to the universe. Geodesics tending backward in an expanding universe must actually converge, forming a singularity. Time itself cannot be tracked after this point, which suggests that time actually originated during the Big Bang. Hawking and Penrose later developed these ideas together, publishing them in 1970. Perhaps now is the time to say that the singularity theorems are most likely erroneous, or at least lead to errors. They give us predictions of pure general relativity and take into account various energy conditions. We know that general relativity is not yet a complete picture, and it is precisely this understanding that is the greatest shortcoming of the singularity theorems. Their way out of the situation may be the union of general relativity and quantum mechanics, the theory of quantum gravity. Such a theory could really tell us what actually happens to geodesics when they collide, and even what geodesics, space, and time actually are. Penrose and Hawking have given us a roadmap to this currently undiscovered theory. Roger Penrose received this year's Nobel Prize in Physics for his contribution to the theoretical understanding of black holes. He shared his award with Reinhard Genzel and Andrea Ghez, who proved the existence of a supermassive black hole in the center of the Milky Way by studying the orbits of stars in the central region of the galaxy. The work of Genzel, Ghez, and other astronomers confirmed the existence of black holes, which means that there really are places in the universe where general relativity must allow for the existence of singularities. All these incredible discoveries came from thinking about how light rays behave when they collide and end up in the dead ends of space-time. The Moon, mysterious, alluring, and enigmatic, Earth's only satellite and our constant companion. It seems that it has been studied inside and out. People and probes have landed on the Moon, scientists have samples of lunar soil, and they have even tried to grow some Earth flora there. The dark side of the Moon is no longer a mystery, and in general, we know practically everything about it. But what questions still remain for humanity? What if these questions are the most important for us? After all, the Moon's influence on Earth is much greater than you think, and it is not at all limited to the connection with tides and sleeplessness during a full moon, as you are accustomed to believing. What if we try to answer the most important questions about the Moon? How did it appear, and where did the samples of terrestrial rocks on its surface come from? Is it true that without the Moon, life on Earth would not have been possible in principle? And what if, instead of the Moon, there were other planets of the solar system? Fasten your seatbelts. We're traveling through time to see a planet that humanity has not yet seen, to witness a catastrophe of cosmic proportions that possibly gave rise to life on Earth and gave us our satellite, and to find out how important an influence the Moon has had on our Mother Earth. First, let's recall what we know about the Moon. The Moon is a relatively large satellite in relation to the size of the planet. Its diameter is 3,474 kilometers, while the diameter of the Earth is 12,742 kilometers. Such proportions are a rarity in the solar system. A truly large moon exists only for Pluto, which recently lost its status as a full-fledged planet and became a dwarf planet. As for the Earth, planetologists believe that the moon stabilizes our planet's orbit and, in particular, the tilt of the rotation axis, which forms the seasons. Some believe that without the moon, the tilt of the rotation axis could seriously change over several million years. This would lead to instability of climatic conditions, which would make the environment less favorable for the development of life. In addition, the presence of the moon has significantly changed the length of the day. Let's also not forget that the moon, due to its reflective ability, gives us illumination at night, and its magnetic forces help regulate the level of world oceans. The Apollo program made a huge contribution to the study of the moon. Samples of lunar soil were delivered to Earth, a real treasure trove for those who really wanted to learn more about the origin of our satellite. One of the most surprising discoveries made by scientists in this area was the fact that the composition of this soil strikingly resembles the composition of the outer layers of Earth's rocks. For example, if we take an element like oxygen and look at the prevalence of its isotopes, we can conclude that their composition is almost identical in lunar and terrestrial soil. If we try to compare terrestrial soil and, say, Martian soil, their composition will be radically different. Another important discovery was the high degree of melting of lunar rocks compared to terrestrial ones. It seemed that lunar rock was subjected to extremely high temperatures and lost elements capable of easy evaporation. What could this indicate? Could it be that the moon was once part of the Earth? Moreover, this suggests that the process of the moon's formation is associated with some extremely destructive phenomenon, namely, a collision of our Earth with some massive celestial body. Is it true that the moon appeared in this way? There are several theories about how the Earth acquired its faithful pale satellite, but the most likely of them is called the giant impact hypothesis. According to this hypothesis, several billion years ago, an object comparable in size to Mars crashed into our planet. Since the impact occurred tangentially, otherwise the Earth would simply have exploded, this object either flew off into space after hitting the Earth or went into it entirely, plunging inside. Chunks of magma rock ejected by the Earth as a result of the impact ended up in near-Earth orbit, and there, over millions of years, they gathered into one object, which, thanks to rotation, acquired a spherical shape. What if this collision hadn't happened? What if there were people on the planet at that moment? Let's go back about 4.6 billion years ago, when hundreds of very young planets began to form around a new star, our Sun. Among them were the tiny Venus and Earth. Their trajectories were significantly different from the present ones. They were more chaotic, so collisions simply had to occur. Imagine a race without rules, a bunch of cars at different speeds driving in a circle. In our case, around the young Sun, they overtake each other and very often collide. Earth and Venus succeeded in this race. They became real devourers of smaller planets. These planets were similar at the very beginning of their life path, but something happened that made the two sisters completely different. This something was the collisions with other celestial bodies that Venus and Earth experienced, and that essentially forever changed the fates of the two worlds. So, two objects crashed into Earth and Venus, and both of these impacts had enormous consequences for both planets. What happened? The impact that occurred on Earth made the planet rotate faster, spinning it up, and thanks to this, a strong magnetic field formed around the planet, which gave the planet protection from most of the solar radiation, which allowed life to develop on Earth in the future. Also, thanks to this impact, the Earth acquired its axial tilt, which caused the occurrence of seasonal changes. Did the same thing happen to Venus? And could life have also formed there? Alas, no. When a similar object, but larger in size, crashed into Venus, its impact not only managed to stop Venus's rotation, but also made the planet rotate in the opposite direction. Moreover, its rotation is almost 243 times slower than the Earth's. How could this catastrophe affect Venus's future? The fact is that the speed of the planet's rotation became insufficient for its core to begin generating a strong magnetic field. It turns out that Venus's surface remained defenseless against the constant flow of particles ejected from the Sun. The hypothetical planet that hit the Earth, which later became the Moon, is called Theia. It is believed that the collision of the Earth and Theia was the last serious catastrophe that our planet experienced. Can you imagine what would have happened to us if a planet of a similar size collided with Earth now? One thing is certain: there would be no chance of survival for humanity. A wave of fire would completely burn the atmosphere, and pieces of the two planets would later begin to form a new world in which there would no longer be a place for humans and all the life forms that had inhabited the Earth until that moment. We would certainly not want to experience such a catastrophe, but in practice, we should undoubtedly be grateful to Theia, because without the moon, life on our planet would have been radically different from what we have now. Many specialists even question the possibility of the development of life on Earth without the presence of a natural satellite with parameters corresponding to our moon. This is part of the so-called rare Earth hypothesis, which we will definitely discuss in the following episodes. For now, let's try to imagine what it would have been like if other planets of the solar system were in the place of the moon. In the case of Venus, due to its large size and amazing reflective ability, we would have had nights comparable to our present early twilight. Moreover, Earth's sister would hardly be able to become its satellite. It is too large. If Venus were to move around the Earth at the same speed as the moon, sooner or later the two would collide, and we would get a new catastrophe. Almost the same applies to Mars. If you were unlucky enough to be on planet Earth at the moment when Venus or Mars turned into a natural satellite of our planet, you should be prepared for catastrophic consequences. Tsunamis, a sharp rise in sea level, a catastrophic increase in the sunlight reflected by the satellite. Let's not forget about changes in the trajectories of the two planets. Although, in the case of Mars, some specialists admit the possibility of the Earth and Mars rotating in a kind of mini-planetary system in a certain balance without collisions and large-scale cosmic catastrophes. But what would happen if the size of the possible satellite exceeded the size of the Earth? Our planet, being at a small distance from Jupiter, would itself become a satellite of the gas giant. The terrible force of the giant's attraction would destroy our planet, gradually grinding it down and capturing it piece by piece. Almost the same fate awaits us in the immediate vicinity of Saturn. Therefore, it is worth being glad that next to us is our small and cozy moon. What else has it done for Earth besides the very fact of its appearance? Surprisingly, there is an opinion that our planet's satellite made a decisive contribution to our existence, and this is not about the catastrophe that made the Earth rotate faster. How so? Remember that the moon is responsible for the tides of the world's oceans. Scientists believe that tides were the impetus for the emergence of life on Earth. When the substances present in the early oceans were mixed with water, special conditions were created in the tidal zone. Then, the water evaporated under the influence of the sun, and during the next high tide, the water returned. In these conditions of wetting and drying of rocks, what would much later become life began to form. From simple substances under such conditions, very complex molecules appeared. RNA, one of the fundamental components of living cells, could have first arisen thanks to the tides. Controlled by the moon's movement, the tidal zones were real chemical laboratories where life itself was bred. Perhaps this will sound silly to a modern person, but having learned so many remarkable facts about our closest cosmic neighbor, one cannot be surprised that for centuries, the image of the moon has been deified and immortalized in the culture of world civilization. But even now, we can look at the lunar disk or crescent with gratitude and curiosity, because who knows how many wonders are hidden in this enigmatic, so close and simultaneously so distant celestial body. The year 2020, thankfully, is over, and for many, this in itself was a desperate dream. Consider devastating forest fires, military conflicts, an unprecedented locust invasion, horrific plane crashes, sudden deaths of famous people, an economic collapse, mass animal deaths, uncontrolled protests, and, to top it all off, a raging pandemic, the new plague of the 21st century. Truly, 2020 was akin to a curse. But is that all? Who said that in 2021, all misfortunes would cease as if by the wave of a magic wand? Let's remember what was planned for 2020. Godzilla's invasion, an asteroid attack, the strongest magnetic storm in the history of the planet, a catastrophic supernova explosion. Stop this, unfortunately, is not a joke, and the probability of this event was not limited to the past year. At the time of the creation of this video, No star has exploded yet, of course, but what is the probability that this cannot happen tomorrow? Is this another fake, or a quite probable event? Which star are we talking about? What will happen to Earth and all of us if something like this happens? Let's imagine that a nearby star explodes. The most fatal consequences of a supernova explosion for the surrounding world, which includes Earth, are a powerful gamma-ray burst. Even the minimal damage consists of a significant reduction in the thickness of the ozone layer due to the oxidation of molecular nitrogen in the atmosphere. Accordingly, the Earth becomes defenseless in the face of ultraviolet threats and bombardment by cosmic rays. This inevitably affects the planet's biosphere. Some scientists are sure that it was nearby gamma-ray bursts that contributed to the extinction of the dinosaurs. But phytoplankton and the most voluminous living organisms on Earth, coral reefs, are particularly affected. And what will people feel, and how will this affect us? A fatal increase in solar radiation? I don't even want to think about it. Naturally, after such an event, all food chains will never be the same, and the consequences will be completely unpredictable. In the worst case, the